When you have a thermal analysis and want to define the material's behavior and properties, which the Abaqus CAE cannot support, you need to use the UMATHT subroutine. Watch this video till the end to learn more about this and what this subroutine can do for you.
So let's cut to the chase and answer the question. What is the UMATHT subroutine? As we said earlier, the UMATHT subroutine is for defining a material's thermal behavior in a thermal analysis. When you have a thermal analysis and want to define the material's behavior and properties which the Abaqus CAE cannot support, you need to use the UMATHT subroutine. It is like UMATH, but the UMATH is for defining the material's mechanical behavior. Let's make an example to better understand it. This figure represents a rectangular piece of wood which, as you see, is on fire. So, what happens when a piece of wood is on fire? It burns and converts to char, which you can see this conversion in this figure. The gray parts represent the char, and you can see the temperature distribution. After 30 minutes of fire exposure, this is what happens. At high temperatures, the wood undergoes pyrolysis and it is converted to char, vapor, and gas, resulting in a reduction in the wood's density. The gas undergoes flaming combustion as it leaves the charred wood. Simulating this phenomenon and having accurate predictions of the realistic temperature distributions is a complex job. You must consider the evolution of the temperature gradient and a bunch of other stuff about thermal analysis. In fact, you need to apply this equation to do this simulation. Obviously, the Abaqus itself cannot do this job alone. Therefore, we must use the UMATHT subroutine. This example was done in a research which you can learn more about it from reference number 1. We will show you the references at the end. Now I think you understand the use of this subroutine. As we've promised, these are some other examples of this subroutine usage. All of them are research articles and we'll show you their references at the end of this video. Now let's see when we have users. What's up? We are here with the first workshop of the UMATHT subroutine package. So let's get right to it. In this workshop, we're going to model the thermal behavior of a steel ruler with the UMATHT subroutine. Here you can see heat flux distribution in the model. This might be a simple simulation, but make no mistakes. Learning something requires taking small steps first. First things first, let's see the geometry of the model. This figure shows the model's dimensions and the model type is 2D deformable. This model contains 10 elements and 22 nodes, and the element type is DC2D4. Next, let's see the material properties. We have a density equal to 7,800 kilograms per cubic meter. Conductivity equals to 1.4 watts per meter per Kelvin. And specific heat equal to 260 joules per kilogram per Kelvin. There are two ways to define these properties in the Abaqus. One way is a traditional one using Abaqus CAE as seen in this picture. The other way is using the subroutine. You must go to the General tab and select User Material. Then select the thermal option from this combo box displayed in this figure and insert the thermal constants. In this simulation, we'll use both ways. So we would have one model without using the subroutine, which is used for verifying, and another using the UMATHT subroutine. Don't worry, you'll better understand when we're explaining the modeling and subroutine. Now let's see what the boundary conditions are. This is our model. We would name the temperature of the top surface T surface. And there is the temperature of the environment, T environment. Suppose a hot wind blows to the top surface and it's gonna warm up the model from the top surface to the bottom. But the question is, how are we gonna apply this hot wind to the model? Well, we'll use the surface film condition from the interaction module. This interaction uses this equation to apply heat or cold due to convection to the surface of a part by surrounding fluids, which in our case is heating. Now let's see what these parameters are. HF stands for heat flux and its SI unit is watt per square meter. H is the heat transfer coefficient, or would be called film coefficient in Abaqus. Its SI unit is watt per Kelvin per square meter. And delta T is the temperature difference. The delta T is the difference between the surface and environment temperatures. The film coefficient will not be constant and varies according to this diagram. It's 10 when the surface temperature is 0, and it increases as the surface temperature increases. You can define this behavior using the interaction property as shown in this picture. Now what about the temperatures? The initial temperature of the model would be 0 degrees Celsius, which means the initial temperature of the surface is also 0. The environment temperature changes according to this diagram. At first, it's 100 and increases as time passes. You must define these values for the sink temperature in the Abaqus. Don't worry, you'll better understand when we get there. Well, these were all the initial conditions you needed to know to start the simulation. We've told you there would be 2 modeling. Now create a job for the subroutine model. In the Edit Job window, go to the General tab and call the subroutine. Click OK and submit the job. Now let's see and compare the results of both models. Open both results. Create another viewport and align them vertically. So here we have the Abaqus model results in the left viewport and the subroutine model results in the right. Now select the Link Viewports option from the Viewport menu to link the viewports, so we can see the results in both models simultaneously. First, let's see the temperature gradient vector at integration points. As you see, both models show the same results, meaning the subroutine works just fine. Also, we can see the heat flux vector and nodal temperature results. You can see that these results show a good agreement as well. Now it's time to open the log file of the subroutine model job to see the prints we specified in the subroutine and see how the subroutine proceeds. The first thing you need to know about this log file is you might get panic when you see it. Just kidding. But seriously, don't worry because we'll walk you through it. The first thing is that we would have this set of data for each integration point in each increment. There are 36 increments and 10 elements, and each element would have 4 integration points. Therefore, in each increment, there will be, for example, 40 U, 40 D temp, and so on. Now, because there is so much data here, we will explain the data of all 4 integration points of the first element at the beginning of the analysis and in the first increment. So, let's begin, shall we? At the beginning of the analysis, nothing has just happened yet. So we expect to see no changes in the variables. Therefore, the time is 0. The D time has a value near 0. We are in step 1. Now, no time has passed yet, so the increment number indicates 0. The du dt has a constant value, which is shown here. The du is 0 as expected. The D temp is obviously 0, and the temperature equals 0 because the initial temperature was set to 0. The NPT and NOEL equal 1, meaning we are in the integration point number 1 of the first element. The coords variable indicates the coordinates of the current integration point. The U is 0. The dudg is 0 because we didn't define anything for it in the subroutine. Because we said that this term is typically 0 in classical heat transfer analysis. The dfdt is also 0 because we didn't define it, so by default it's 0. The number of spatial gradients of temperature is 2. This data set indicates the loop that calculates the heat flux vector. The I is 1, and these two variables are 0 because we are at the beginning of the analysis. The I is 2, and again we have 0 values. So the heat flux loop is finished. This data set indicates the loop that calculates the dfdg matrix. When the I equals 1, the first component of the matrix main diagonal will be calculated. Therefore, you can see that only the first component has a value which equals conductivity. When the I equals 2, the second component of the matrix main diagonal will be calculated, which you can see here. So, these data were for the first integration point of the first element at the beginning of the analysis. The other integration points of this element would have the same values at the beginning. These data are for the second integration point. And you can see the NPT equals 2. There are its coordinates, and you can see the rest here. These are for the third integration point. And there is the data for the last integration point of this element at the beginning of the analysis. Now let's see how these variables change as time passes. Now we are in the first increment because the kink equals 1. The D time equals 100 because we set that in the step module, meaning the time has passed. And now we would expect changes in the variables. The du dt has a constant value that equals a specific heat. The du has this value, which if we multiply the du dt and the d temp, this value will be obtained. The NPT and NOEL equal 1, and you know what that means. There are the coordinates of this integration point. The u has the same value as the du because the previous value was 0. These two variables are 0 because of the reason mentioned before. And we expect them to remain 0 for the rest of the analysis. And the NTGRD equals 2. Now let's see how the heat flux vector is calculated. When the I equals 1, this vector's first component will be calculated. So according to the subroutine, when the conductivity is multiplied by the first component of the dTEM array, the first component of the heat flux vector is calculated. And when the I equals 2, the second component will be calculated. The DFDG matrix calculation would be the same as before. Here you can see the values of the second integration point of the first element in the first increment. The explanations of the other two integration points are the same, so we skip them and just show you their data. Well, that's it. We hope we have explained this tutorial as best as we could so you can understand how the UMATHT subroutine works. Thanks for watching.
Hello everybody and welcome to our new video training package of Abaqus, UMATHT subroutine in Abaqus. This package includes these sections. Lesson: Introduction to UMATHT. Workshop 1. Modeling thermal behavior of a steel ruler with UMATHT subroutine. Thank you for taking the time to watch this video. We hope it will be useful for you.